think we can start. Yeah? Okay, so we start with one of the first sessions here. We have 4 speakers today, advancements in lithium-ion batteries generation 3B. How many of you are from the research? Many? How many from the industry? A bit less, but still. And from public representative? 1. Okay. Good. So we have today 3 Horizon 2020 projects and 1 Horizon Europe project, a little bit following what was done in the Horizon 2020 projects. 2 projects finished, so we will see the results. 1 almost at the end, and the last one, I would say, halfway. So we will have a little bit of different perspectives. My name is Monica Giannini. I welcome you to this session. I work in CINEA, in the Horizon Transport Unit. I deal with batteries, electric vehicles, e-powertrains. And today, I'm very happy to have 3 of my projects, and another one that is related to the 3 projects. Very challenging projects. We have also policy officers here who can confirm that this was a very, very challenging topic, and it continued to be. We will see some results, but we will also see, and we will ask our coordinators for lessons learned and what are still the open points. What will be future topics for research coming out from the work that they have done. I would say that following this intensive work done in this project, I have seen a lot of issues. It's a very, very challenging sector. And these projects were asked to combine and to solve a number of issues all together in terms of performance, in terms of stability, in terms of cyclability, in terms of costs, replicability, and so far, so on with the long list. So we will see what they were up to. I think this is still an open topic, and I think that one of the most important aspects that I would like to ask our coordinators to share is really what they have learned, the lessons learned from the work that they have done. So I would like to start with the first project, 3Believe, and I would like to ask Boshidar. So I don't have my glasses, but I know Boshidar. So European Research and Innovation Project Coordinator at AIT, the Austrian Institute of Technology, currently coordinating 3Believe, but also another project that came after 3Believe, and it's learning from 3Believe and following up. You will mention HighSpin. Past research and innovation actions include projects in battery research as well as for electric mobility in urban goods delivery. Boshidar has a background in business management, renewable energy, and environmental sustainability management. So the floor is yours. Boshidar, you can come here. I would like to ask if you have any immediate question, any immediate reaction at the end of each presentation, you can raise your hand, but we will have some time for questions and answer at the end, also with the support of a colleague from VUB. You maybe want to introduce yourself just for technical coordination?
Yeah, definitely. Yes, welcome everyone for this session. My name is Burak Dermenci, working as a senior researcher in VUB, Free University of Brussels. So yeah, we will also, during the question and Q&A session, we will also have, you will all have chance to ask the questions, very specific questions for the project related and presentation related things. So you can also keep your technical questions inside, but if you need something to clarify before going into that, of course you're free to ask.
Thank you. So Boshidar, now it's your time, sorry. I leave you the can also advance with these or go back, but never press ask.
Okay,
thank you.
Never press ask. So, all right, so thank you very much for the introduction. Ladies and gentlemen, honorable session chairs and policy officers, it's a privilege and a pleasure to hold the first presentation for this Horizon 2020 project. So the 3Believe project was conceived almost 5 years ago today. It was answering to the LC-BAT 5 2019 call that Monica already mentioned. This call was challenging because it focused on 3 areas. So one was cell chemistry and cell morphology. The second domain was sensors and sensing. And the third pillar was manufacturing, and sustainability was a cross-cutting topic across all of them, I would say. So our consortium of 21 beneficiaries elected to answer to all of these aspects to have a most integrated view of this 3B manufacturing technology, or this 3B cell technology. So with the exception of raw materials extraction, we have covered actually practically the whole value chain of the battery. So starting from active materials development, cell manufacturing on 3 levels, so lab, small pilot, larger pilot, development and integration of sensors in and on cells, also development of BMS, then integrating these 3B cells into appropriate modules and packs, testing them in first life, testing them in second life, and also looking at what does it mean for recycling when you have a technology or a cell chemistry that has no cobalt inside. So the work was clustered around 5 specific objectives. So the first, of course, focuses on the cell chemistry itself, so to develop a cobalt-free lithium-ion battery for hybrid electric and fully electric vehicle applications. So what we were focusing on here was to combine a lithium nickel manganese oxide cathode, a silicon graphite anode, and a high voltage electrolyte. And the performance targets were taken directly from the call, so high volumetric energy density of 750 watt-hours a liter, fast charging capability, and of course long cycle life. The second objective was to do with sensors. So here we took 3 approaches to try to dynamically monitor the state of the cell from the inside and from the outside and on module level, to have a more dynamic and quicker understanding, and hopefully in this way increase the lifetime and usable energy of the battery. Under objective 3, we looked at quality control of the manufacturing process. So this is to do with inspecting the quality of the coated electrode foils to understand process better and to improve yields in the manufacturing. Objective 4 was to demonstrate the battery technology, so incorporate the 3B cells into modules and packs, and also, very importantly, to demonstrate the upscaling of the production process to gigawatt-hour per year scale. So here we modeled 10 gigawatt-hour per year production. And finally, we wanted to understand the whole process from end to end through life cycle analysis and life cycle costing, so looking at the environmental and economic aspects of this chemistry. So for all of these, I'll try to give a cross-section. I will be very brief, we have only 1 slide for each result, so excuse me if I go a little bit quickly, but maybe we can cover in the questions and answers afterwards. Okay, so for the cell chemistry work, for the cell optimization, what we did is we selected various active material candidates, so 5 LNMO candidates for the cathode side, in total about 10 silicon graphite candidates with different particle size distributions, silicon content ranging from 15 to 40%, and different dopants, and a high voltage electrolyte. So when we look in the top left, so cycling in half cell, the LNMOs had quite a good cycling stability, ranging from 86 to about 95% capacity retention over 1,000 cycles. However, the difficulties or the challenge begins, of course, when we combine them in a full cell. So here it was possible on initial cycling to achieve 480 watt-hours per liter, so fairly far away from the target. But the key aspect to note here is that there's a rapid capacity fade in this combination of materials. So we have 80% in under 50 cycles. The main driver for this was identified as cyclable lithium loss. So the cyclable lithium is bound up irreversibly. We have tried to mitigate this through various measures, so playing with formation protocols, upper cutoff voltages, and also electrolyte tailoring, so working with electrolyte solvents, additives, and salts. However, although there were some promising improvements in the initial cycles, after a while they converge, and the loss of cyclable lithium can't really be mitigated, at least not with these approaches. What we have also seen is that in the larger format, there was some significant gas formation. So we started seeing these effects from 5 ampere hour scales, 5 ampere hours, and then definitely also on 30 ampere hours, gas formation, which was not visible on smaller formats. And this points probably to a dissolution or to an unwanted decomposition of the electrolyte. So clearly there's more work to be done in this 3B cell chemistry from our perspective, and I can talk afterwards also about the follow-up project. Moving to the second objective, so here we looked at 3 different approaches for cell sensing. So on the left is in-cell sensing with a fiber optic based sensor. Then there's on-cell sensing with a multi-measurand, so this measures electric impedance, strain, gassing, liquids, and of course also temperature, voltage, and current. Then there was a module level sensor that was further developed and integrated into the heart of the BMS board, an open source battery management system, as the key controller. And all these 3 sensors here were made to communicate via common protocol, and now this board is available as an open source development platform. Also an advanced operating algorithm was implemented that tries to combine different SOC estimation strategies. And this is available as a C code for application into any kind of BMS. Briefly, we can say that for the internal sensor, we found that so it was possible to integrate this in a leak-proof way into the cell, but more work is needed to be done in order to understand the exact correlation of the optical measurements with the electrochemical cycling. And in fact, the work was rerouted towards laboratory equipment on this. On this sensor, this is actually further developed in other projects, so made very good progress. On the quality control side, so here we wanted to look at the coating of electrodes on the pilot coating line and to detect any faults that could impact the performance of the cell later on after it's been manufactured. So what was developed here is an inline inspection system on an optical basis, so both in hardware, as you can see over there at the end of the line. And what we did is we sampled deliberately some possible coating defects that can happen in the coating stage, so agglomerations, cracks, cavities, blade trails. These were captured optically and annotated by hand, and this data was used as training to train a machine learning algorithm that should then detect on new electrodes the results. So you can see this here with detection of false positives, false negatives, true positives, true negatives, etc. So one outcome is that it was possible to improve the scanning resolution from 50 micrometers to 10 micrometers and to improve the speed at which this system works from 0.5 meter per second to 2 meters per second, so bringing it approximately to an industrially usable point. Probably more work is needed in terms of training data to actually give the algorithm more food, let's say, to be trained on, but in principle, this is already working quite well. Yes, here's an aspect that I personally found extremely interesting. So we asked ourselves, okay, now we have looked at this cell technology and this chemistry on smaller scales, but what would it mean? Let's say that the chemistry actually worked well in a cell, which is of course still work to do. What would it mean to manufacture this at a scale of 10 gigawatt hours per year? So a small gigafactory actually, as these things go. And so we have moduled the cell manufacturing process in 2D and 3D in a plant simulation software. So something that's really used in industry. So looking at these various processes, you know, electrode production, cell assembly, cell finishing. And what you see is the finished factory floor layout. What we should say is that the modeling was done on a bottom-up basis using real machines, so incorporating all the states, the energy requirements, the footprints, the downtimes, the failure rates, all these kinds of things. And of course, there are very many interesting things that you can learn from this. I won't go through all of these numbers, but for example, 2 or 3 interesting key figures that we found is that just from a cell production perspective, it takes about 42 kilowatt hours of production energy to produce a kilowatt hours worth of storage of cells. The investment cost is about 60 million euros per year per gigawatt hour. Yeah, so 600 million for 10 gigawatt hours. And the floor and the factory occupies about 80,000 square meters. But of course, there are lots of other metrics that you could take out of something like this. The next step is to assemble the cells into modules. So here, very quickly, there's the module line assembly concept where pick-and-place robots take the cells and incorporate them into modules, a small mock-up of which you can see here, but this is not including the cooling system and the expansion system. And then finally, the final step is assembling the modules into packs. So here you have robots across 7 stations, I think, that take the modules and assemble them into packs. And again, we can calculate, okay, what's the footprint, what's the takt time, the energy consumption, and so on to assemble 10 gigawatt hours worth of packs per year. And I might say, I think, as far as we're aware, this is quite unique in the battery program, in the Horizon work program, this kind of modeling, as far as we know. So then, importantly, we asked ourselves, how, after the use in first life, what can scenarios for second life look like? So we have looked at a second life application using the end-of-life battery in a stationary energy storage application coupled with PV. In an island electricity grid. And we have looked at scenarios where either the pack is disassembled down to the module and reused, or where the whole pack is used directly as energy storage. Not time to go into the details here, but this was all incorporated, all this and the previous steps were incorporated into the life cycle analysis and the life cycle costing. And so we can maybe summarize a few takeaways. So, first of all, according to the LCA from an environmental impact perspective, LNMO has the potential to decrease environmental impact versus NMC 811. So you can see it in the bottom right graph. So if you look at the indicators along climate change, particulate matter emissions, fossil fuel depletion, and use of minerals, there are some improvements against the theoretical NMC cell. Of course, it depends on some assumptions, but there seems to be potential here. Second important finding that we made is that the call asked to achieve a manufacturing cost of 90 euros per kilowatt hour at pack level. This we could not achieve in the modeling, so we came down to 138 euros per kilowatt hour. That could be confirmed based on the assumptions and modeling in the project. But 90 euros per kilowatt hour remained out of reach based on the modeling that was done in this project. We can also say that use in second life of a spent battery is definitely environmentally beneficial. So from an environmental and resource point of view, there are clear benefits. However, the economics of this depend highly on the configuration of the intended second life application. So what is it exactly that you want to use it for? And secondly, also on the diagnostic and reconditioning cost. Finally, we can say that the economics of recycling itself can be impacted by the absence of cobalt and lower nickel content, because these are valuable materials, of course. So just briefly on the recycling study itself, as I mentioned, because this is a cobalt-free chemistry, it was interesting to look, okay, what does it mean to recycle this? So here at lab and pilot scale, a thermomechanical and hydrometallurgical process chain was developed. The thermomechanical part is state-of-the-art, more or less. The hydrometallurgical part looked at how to precipitate the nickel and manganese in the absence of cobalt, which is often a catalyst and useful in this process. And it was shown this is possible. So the original targets were to obtain a recovery rate of greater than 50% for the valuable metals. and to reduce the reagent quantities, so hydroxides, acids, and things like that in the process, and to have a recovered material purity of greater than 95%. In principle, we can say these are achievable targets. In the initial results, we were only limited a little bit by the cell quantities, so the process was suboptimal. However, there was a very clear statement from the team that worked on this that with a larger quantity and with some slight experimental improvements and process optimization, these are, and in excess of these targets, are achievable for the recycling recovery. Yes, I come briefly to the dissemination part. I'm probably advancing in the time, so I will be very quick on this. So two main points here. One is that we try to have a very large share of deliverables out of this project be public. So we have greater than 70% of all deliverables are public in their dissemination level. And of course, all the papers and publications can be found both on the project website and also regarding the deliverables on Cordis now or soon. Then also an important point that's close to my heart, because we also have colleagues from the other, or some of the other projects here. We had a good clustering and collaboration in the LC-BAT5 cluster. So besides 3Believe, COBRA, SENSE, and Hydra, we worked together on in-person and online events, and I think we all agree that this was a very fruitful collaboration. So this was really a very worthwhile thing, and I think, of course, we will hear some presentations from those projects coming up. Yes, I come already to the expected impacts of the project. The call wanted impacts in technological readiness, in manufacturability, and technological know-how. I have put some of the asks of the call in green text, but I won't read them now. But basically, when we talk about impacts, we think that these come from two main areas. So one is capacity building across the value chain during the project, but also afterwards. And of course, the exploitation of the consortium's results. So we asked our consortium to classify their results by type. So are they data set, knowledge, skills, models, process improvements, etc. And what you can see on the left graph is that by far and away, gain of knowledge and skills was the main type of result that the consortium gained, followed by availability of prototypes or an experimentation with prototypes and obtaining data and data sets. We also asked them how they expect to exploit these results, and we can see that in the near term, so in the next 1 to 2 years, the focus is on further research, so whether that's co-funded or customer research, of course also some product development, and then it shifts over time towards product and service development. And I would actually like to give you a few examples of these things now. So on exploitation, on the route for using the results for further co-funded research, as already mentioned before, some of the learnings and findings, especially on the cell electrochemistry level, are taken up in a direct successor project called HiSpin. So this takes as a starting point the reference materials from 3Believe, the knowledge, but also the cell format, the module design, and the sensor, and focuses directly on electrolyte development, on materials development again, but also on multi-layer coating and laser structuring of the electrodes. And then also one example is the take-up of the multi-measure and sensor in another research project, Matisse, which is on hybrid electric aircraft and inserting multifunctional structural batteries with sensors into aircraft. Then there's also the development of products and services. So here I've mentioned these already. On the sensors, it has actually been quite successful because the optical sensor, there was a product decision made to turn this into laboratory equipment, so the so-called 8-channel analyzer, because the researchers realized, okay, there's still a lot of development effort left and might not pay off right now given the integration effort to put this in cells, but as laboratory equipment, they were actually able to make decisions quite quickly. Then also on the active materials supply, this is just an example that one of the partners in the project, one of the materials suppliers, is cooperating also with a battery manufacturer to further push the LNMO technology, so both with other anodes and also with graphite anodes. So of course this is not a direct output solely of this project, but projects like this one contribute. And then I come to the last expected impact, maybe a cautionary note. One expected impact was the reduction of critical raw materials with regard to NMC or compared to NMC. And of course, we can see, yes, with LNMO, we can reduce 100% of the cobalt and about 60% of the nickel. However, we have to keep in mind that there's a substitution going on for manganese. So the manganese is also on the list of critical raw materials. Maybe it's just a SRM. So it's definitely an improvement, but it's not a magic, let's say, solution. And therefore, we have to be careful about our supply chain. I think this is a very well-known point. Here I give just an example about current discussions internationally on seabed mining. So you can see a manganese nodule here in a deposit on the bottom of the sea, where there's talk about making this commercially feasible. So we have to watch out not to achieve greenhouse gas emissions reductions at the expense of habitats and biodiversity loss. Then, and I'm on my final slide, we were asked to share some lessons learned. I will pick out only 2 of them here. So one was that the ambition of the call was high, so the integration of a number of points, so cell chemistry based with, combined with integration of sensors, manufacturing aspects, and sustainability was a lot. So each of these things by themselves are tractable, but to serially connect them together in one call in the given amount of time was very challenging. So then the last point here is that, of course, it's important to focus on a functioning cell chemistry. So here, doing an early scale up as soon as possible is critical, because as we mentioned, you see some effects of the cell chemistry only at larger scales. Yeah, so it's nice and necessary to work on coin cells, but as soon as possible, given limitations with equipment availability, etc., minimum material amounts, scaling up to larger systems is important. And then finally, and then I'm finished, is that, I haven't put it on the slide here, but the work that's going on now on battery passport, we think is very important, because we have seen that the the economics of using batteries in second life depends very much on having a low diagnostic effort. So I think with this, I leave it for here. Thank you very much for your attention.
Thank you, Boshida. Any immediate reaction to this presentation? Otherwise, we go on with the second speaker, and we leave questions for the end. Thank you. Thank you very much. So we go with the second, Ruben, who will present as Project Sense.
Yes.
I think we just go on, voila, and then we click on here, voila. So Ruben Kühnel is a staff scientist at EMPA, so the Swiss Federal Laboratories for Material Science and Technology. Sorry, yes, you're right, otherwise, yes, yeah, sure, thank you, sorry. And technology, he holds degrees in chemistry and business chemistry. That's interesting, business chemistry. And conducted doctoral studies at the MEET Battery Research Center at the University of Münster in Germany. And since 2020, he has been the technical project leader of SENSE, Horizon 2020 project, in Generation 3B lithium-ion batteries. His main research interests include the development of liquid electrolytes for lithium-ion and alternative battery technologies, interface characterization, development of formation of protocols, as well as research automation. Next year I will bring my glasses. Thank you, and the floor is yours. 15, 20 minutes.
Okay. Yeah, thank you very much, Monika, for the kind introduction. Yes, the SENSE project. So, same call as Boshida's project, of course. And in terms of duration, it was a 4-year project. We just finished the project actually last week. So the just ended. The budget of the project was 10 million. We were 11 partners, 6 research institutes and universities, 3 large enterprises, and 2 SMEs. And the project was coordinated by EMPA in Switzerland. When we submitted the proposal that was still possible in Horizon 2020. Objectives and RNI areas, of course, quite similar to the 3Believe project, but I would say we put probably a larger emphasis than some of the other projects on materials development, but we also included some sensor development, aqueous electrode processing, as well as cell and module development. Boshida already mentioned, and Monica also mentioned that before, the scope of this call was really quite broad, which was a challenge for us. In terms of demonstrators, we built 10 ampere hour pouch cells with in-cell sensors, as well as a 12-cell module with a smart cooling system. The cell level objectives, we also took them from the call, same as in the case of 3Believe, so really high volumetric energy density, fast charging capability, a 20% reduction of critical materials, and probably the most challenging one for all the projects was really really long, to achieve a long cycle life with silicon-based cells. In terms of cell chemistry, on the cathode side, we went for nickel-rich NMC, which is a little bit more established than LNMO, and actually allowed us in the end to reach the target energy density. Now I would like to present you some highlights from the project, starting on the cathode side. As you probably know, when you go to high nickel contents, capacity nicely increases of these layered oxide cathode materials. Also, you can bring the cost down, as nickel is, I think, currently less expensive than cobalt. But on the other hand, you lose in stability. So we follow different approaches. I mean, the standard approaches, coatings, dopings. And here I'm showing you an example of a substitution of some of the manganese by magnesium. And in that way, we were able to basically achieve similar capacity as for NMC 811, but significantly lower cobalt content of 5% instead of 10% by substituting 2% of the manganese by magnesium. So here in dark blue, you can see we achieved a really nice cycling stability. And in general, for this cell chemistry, you are rather limited on by the anode side. The cathode material was then also scaled up by our project partner ZSW from Germany for the prototype cell. So we produced around 20 kilograms of a layered oxide cathode material in the project. Here an example on the anode side. As you probably know, silicon undergoes this really large volume change, and in each cycle you consume a lot of lithium because you always have to reform this protective layer that you need to suppress the electrolyte decomposition. And one way to mitigate these lithium losses is to pre-lithiate the material. So what that basically means is you introduce some lithium in the anode, even in our case, before assembling the cell. So we prepared a chemical bus containing lithium, and then we inserted the electrodes, the negative electrodes, in this chemical bus and pre-lithiated the material. And in that way, you form a kind of reservoir of lithium, and you can then really nicely extend the cycle life. So you can see here on the right side in purple, the cell without any pre-lithiation showed really rapid capacity fading, but with the pre-lithiation we could really achieve a kind of stable capacity here for more than 100 cycles. Before then probably the reservoir of lithium was depleted, and then we got into the fading regime again. But that was quite a nice result, and very recently, last month, we managed to upscale this technology and to also demonstrate it in small pouch cells, because these are coin cell results here, but we now also managed to upscale it to 2 ampere hour pouch cells, which was quite a challenge because handling a lot of lithium metal, and in that case THF in a glove box, it was not that easy, but in the end it worked out quite well. Then we also worked on the electrolyte, and here we gave ourselves another challenge. So we didn't only want to stabilize the cell chemistry, but we also wanted to render the electrolyte non-flammable. But because this call was asking for fast charging capability, we couldn't really go for some of the alternative liquid electrolytes, for example, based on ionic liquids, which are quite viscous and typically have a significantly lower lithium-ion conductivity, and then it's difficult to reach these the project targets. So our approach was to stick to the classical carbonate solvents and to just add some flame retardants to the electrolyte, and we focused on this class of cyclotriphosphazine type flame retardants. And when combining 5% of this flame retardant with a slightly increased lithium PF6 concentration of 1.35 molar compared to the more typical 1 molar concentration, we were able to render the electrolyte non-flammable in terms of its self-extinguishing time, which is the time it takes for the electrolyte to stop burning after you put it on fire, for example, with such a lighter. What was then really nice for us to see is that this electrolyte retained a high conductivity of more than 90% compared to the baseline electrolyte, which was for us really important for the fast charging capability. And what we were then also pleased to see is that also it stabilized a bit our full cells. And we then investigated that in detail. We did some post-mortem analysis, and we found that the stabilization mainly takes place on the anode side. We saw that also the composition of this protective layer changes. It becomes richer in lithium fluoride, which is an important SEI component. And we also saw less volume expansion of the anode compared to the baseline electrolyte. And this electrolyte was then upscaled by our project partner Solver Ionic for the demonstrator pouch cells that we built in this project. When you are at these high energy densities and also for fast charging, heat generation and also heat dissipation are becoming more important. And here our approach was to substitute the standard or conventional conductive additive carbon black by a carbon nanotube based conductive additive with significantly higher electrical and thermal conductivity. So here you can see an SEM image of an electrode. So it also kind of nicely wraps around the particles, and we were really able to significantly increase the electrical conductivity compared to the conventional carbon black based approach, and also the thermal conductivity. And we also built cells with this material, and it also actually ended up in one of our demonstrators. And we obtained also a very similar cycling stability compared to carbon black. And our industrial partner Huntsman in the project just commenced the construction of a 30-ton plant in the US, not in Europe, but still producing this carbon material in increasing quantities. But as far as I know, they're planning to make formulations with this carbon material actually in Europe that they then want to sell to for example, cell manufacturers. As I mentioned before, we also worked on sensors, on in-cell sensors, mainly temperature sensors and reference electrodes. And we also designed and assembled a 12-cell 500 watt-hour module that you can see on this picture here. And because of the sensors in the cell, we are also able to track the temperatures of the individual cells during operation of the cell. And the cooling system can then also really adapt to the increases in cell temperature as necessary. So that was also quite a large effort in the project, also including all the battery management system software work, how to integrate the sensors in the BMS and so on. Boshida already mentioned briefly our clustering activities. So the 4 projects teamed up to form these LCBAT5 clusters. And we had a couple of joint initiatives and activities. For example, we published a joint newsletter. We organized a couple of joint workshops or conference sessions. And last November, we organized a relatively large scientific symposium, bringing together the 4 projects and also made it open to the wider public. And as Boshida already mentioned, in the case of the high-spin project, another project came out of these clustering activities, the Intelligent project, where the 4 coordinators teamed up to build another consortium based on the learnings of the LCBAT5 projects. So I think this is also really something I would recommend for future calls to encourage these clustering activities. Maybe looking a bit at the achievements of the cell level objectives that are listed before. So we actually managed to achieve this quite challenging energy density target of 750 watt-hours per liter. Also, fast in terms of fast charging, we are relatively good. We managed to reduce the content of critical raw materials by 20%. But in terms of cycling stability with silicon, as Boshida also mentioned, this remains really a challenge. I mean, with this pre-lithiation approach that I introduced before, we actually managed to improve the cycling stability compared to what I'm showing you here, but we are still, of course, a bit away from the 2000 cycles. But we managed to demonstrate all the other technologies also in nickel-rich NMC graphite cells, so including the aqueous processing and so on. And those cells, the first generation cells, they're still running, and they now reached 1,500 cycles, and they're still above 80% of the initial capacity, but it really also takes a long time to demonstrate 2,000 cycles if you don't want to go to a really high rate, right? I already mentioned some of the success stories from our industrial partners, right? I already mentioned Huntsman with their production plant, N-Wires, which produced the anode material in our project, a French SME just got a 5 million euro funding from a Korean company, which was for them, I think, quite a significant amount of money and a significant achievement to really scale up the production of their material. And Northvolt was also one of our key partners in the project. I don't know how instrumental we were in their 5 billion project financing, that they just got, but we also wanted to briefly mention that here, the Northvolt so keeps growing. In terms of impact, what I can say for our project, I see a strong educational aspect. I mean, there are quite a few PhD students and postdocs that went through the project and contributed and learned a lot about kind of next generation lithium-ion battery technology. And many of those students and postdocs are now working in the battery field already. And I think this is also an important contribution to the battery ecosystem in Europe. The project enabled some industrial partners to enter the battery market or contributed to it. I gave the examples of Huntsman and N-Wires. The third point is a bit more technological. I mean, we managed to demonstrate that you can really bring the cobalt content down of these layered oxide cathode materials. And of course, the technical results have also been demonstrated and made publicly available in quite a few peer-reviewed scientific publications. We have 10 more in preparation at the moment. And participants or members of the project also attended quite a few conferences or scientific symposia. And we also have a couple of patents that came out of the project. And I already mentioned the follow-up project, Intelligent. Yes, with that I would like to especially thank all the project partners that did all the work in the last 4 years. Was a very fruitful project. It was really a great pleasure to work with all the project partners, and of course, and I would also like to thank our project officer, Monica, for the very good collaboration. And thank you all for your attention. Thank you.
Thank you. Thank you, Ruben. Any immediate reaction question now? So we go on with the third project, COBRA. That stands for Cobalt-free batteries for future automotive application. And we have the coordinator, Jordi Jakasa, PhD in material science at Sheffield University, working on the structural and electrochemical characterization of electrode materials for lithium-ion batteries. Senior researcher at IREC, coordinator of the project, and I will try to summarize a bit. Research aims to develop new and sustainable battery components, especially cathodes, for next generation high energy batteries, including generation 3B. So the floor is yours, Jordi, for COBRA.
Thank you very much, Monica. Let me try this. Let's see if it works. Okay. 15. Great. Fantastic. Well, thank you for the invitation, for being here, for presenting COBRA, and obviously to showing the results of this is very much focused on the results, as you will see. So the project is called Cobalt-free batteries for future automotive applications. Well, the same as my colleagues, so the project is aiming to develop the next generation cobalt-free lithium-ion batteries, and the project is targeting TRL level 6. That means developing of battery packs. Is a RIA project, started in January 2020, and obviously with all that COVID times, it was a little bit difficult, and then it's expected to be finished in June 2024. That includes the extension that we got. The total grant of the project was, or it is, 11.8 million. So, and the consortium is conformed by 19 partners. So we are 3 universities, 7 research technological organizations, 4 small and medium enterprises, and 5 large enterprises. Okay, so as my colleagues have already been through all this, so COBRA as well is tackling the 3 main pillars of the call, which were manufacturing, cobalt-free materials, and an advanced management system and integration of sensors. And to make it a little bit more quicker and not to just spend so much time, so I will try to highlight some of the hot topics, you know, that the COBRA is adding to this to the cluster. So especially in terms of the cathode, so we are developing, or we're looking a new cathode, which is a lithium-rich oxide, aiming to fulfill the target. We are looking at recycled silicon that is coming from the PV industry. The electrolytes, we have very much looking at also ionic liquids and to improve the stability and the safety of these electrolytes. Cell level, obviously the same targets in terms of energy density, very challenging. Fast charging as well. Advanced BMS, here we're also looking at the increasing of the performance, of course. In COBRA, we also have been very much looking at the design of new battery packs. So this is something I will show very briefly, which improving the resistance, improving the strength, and obviously improving the safety of these battery packs while reducing the weight. And in terms of environmentally, of course, you know, following the same line as my colleagues, so reducing cobalt. In our case, we don't have any cobalt, so the cathode material is cobalt-free. Attain 95% recyclability, and obviously promoting the use of green and recycling materials for the battery. And for the last one, you know, probably I want to make some reference at the end of my slides. So the results, let's go straight to the point, which I guess is what we are came here. So what I would want to do is I would be more on these specific objectives we define in our COBRA proposal That would be on the top right-hand side as green ones, the fulfilled ones, and the blue ones, they're the ones that we are working on that, and most possibly is going to be difficult to achieve. So the cobalt-free ones, the new material of oxides that we are working, is a lithium-rich, which is a composite of monoclinic and rhombohedral phrases. This is not so well-known materials as my colleagues, or NMCs or spinels, but personal opinion are very interesting materials, so I'm trying to push them forward in other proposals. So we have been working on all doping scenarios, and we have managed to improve the stability by aluminum doping quite nicely. On this series of figures, you could see like the parent one dope one shows less cycling stability than aluminum ones. And we also were looking at two generations. So one generation one, which is lithium nominal, and let's say in generation two, which is lithium more lithium rich, aiming to increase the capacity. And we managed to extend the cycle life of this parent composition and also to improve the voltage stability. Okay, and eventually we managed to get some of the achievements that were proposed, which was fast charging up to 3C. So we managed to deliver 120 milliamperes hour per gram at 55 degrees. Okay, at the same time as obviously obtaining high capacities of 250 at low C rates. For the anode, we were looking at recycled silicon from PV industry, so which was from the beginning challenging, but also very interesting for improving the sustainability of the batteries. We looked very carefully at the processing conditions of these silicons, and we managed to get high loadings, which is important when you look at the high energy density for the silicon, beyond 4 milliamperes hour per centimeter square, so that was good achievement as well. And we up to a loading of the silicon between 10 and 12 weight percent into the electrode. And on that weight ratios, we were managed to get capacity at 3C, which was also one of the objectives of the COBRA project. Unfortunately, obviously, this silicon, as my colleagues have already shown its cycling degradation is quite severe. Regarding the electrolytes, we have been looking at a large range of electrolyte formulations based on LiPF6, but also LiFSI and also ionic liquids and with additives. For that work package, we had clear objectives of improving the electrochemical stability, so that we did with, as you can see on the central figure, so of using LiPF6 electrolytes with some additives. We managed to get also reduced flammability using ionic liquids with some flashpoint studies of new compositions of ionic liquids. We use obviously that ionic liquids to improve the performance of the electrodes, so to some extent cycle life was not severely improved compared to the carbonate ones, but we had that improvement on safety, which was also one of the requirements. And also we were looking on these work packages because the liquid electrolyte is what makes the connection between the two electrodes. So full cell studies obviously getting ready for like the pound cell fabrication. And on here, just I want to put a personal note. So that studies were done in COINCEL. So for the next projects, I think looking for the specifications in terms of the MP ratio, voltage cutoff, I think we need to go to pound cell straight away, making all that studies at the pouch cell level, because then it is difficult to really translate all these results from COINCEL to pound cell level. Cobalt-free manufacturing, so as you already see the results from my colleagues, this challenging energy density and fast charging for us was difficult, and at some point we have to take some considerations. Obviously, we fabricated our cobalt-free cells with an energy density volumetric one of 400. We decided not to really push that and really go into high loading, because we knew already that it was like not really sensible to really achieve good cycling. So we prefer to focus into the developments of battery pack and sensors. I will show you later. But anyway, we made good contributions in terms of upscaling the electrodes, handling thin current collectors. So we managed to get anodes deposited in 8 micrometer foils, copper foils. That was an improvement for the manufacturing industry. And also 15 micrometers for the cathode, which is quite thin, talking for the aluminum. We were looking, and we will report soon, new improved electrolyte fillings strategies. And obviously, since we have a new cell chemistry, we develop new improved cell formation process. Eventually, we are in the process to finalizing over 250 cells that we are being integrated into modules and battery packs. The battery management system. This is not my topic of expertise, but I will try to do my best. So we have successfully integrated different sensors into this BMS. We have one cell temperature, one strain gauge, one pressure, and one impedance sensor integrated into the BMS. All these are attached at the cell level, so you can see on the right-hand side, on the top part, all these sensors are integrated. The connections between all these sensors are being done wireless, optical-based, and one nice aspect of this BMS that we have constructed, it is decentralized and modular, which means that we can apply not just to the battery pack, but even if we select just a simple module, the BMS can be easily integrated into that. And of course, we have this physics-based modeling, which are in charge of controlling the temperature and the charge management control of the battery itself. Battery pack design. Right from the beginning, we took the decision that what was the proposal, how it was written. So we didn't want to have that dependency of that battery pack to have on the cells and on the material. So what we did is just to, right from the beginning, have a parallel development for the battery pack. We made 2 battery packs, Gen 0 and Gen X, and we managed to reduce the weight of the battery pack more than 50% between the first version of this battery pack to the second one that we produce, and it's going to be including all the final Gen X cells. So that takes that 50% weight reduction. Also, of course, we also wanted to have like the least environmental impact for this battery pack. So we constructed it out from green and recycled materials. So we use aluminum, recycled aluminum and wood with obviously with a protective coating to achieve that lithium-ion battery fires that can go up to 800 degrees. So this has been already achieved as well. Regarding the tensile strength and impact resistance, we have not done the test yet. So hopefully at some point I can inform you about this. And before I forget, we also integrate a laser-based gas sensor to detect the typical gases that are produced in the battery when they go to the thermal runaway, so CO, CO2, and methane, so that can be also, it can be detected at the battery pack level. Validation up to now has been done on Gen 0, the first battery pack I was commenting to you, so we established the profiles for the characterization and testing of this Gen 0, and they have been tested, of course. As you saw before, the boost test on this Gen 0 have been done for the evaluation of the safety. And of course, we have done already the evaluation and characterization of the sensors, and we are going to be releasing in a question of weeks our module with the integration of the 5 sensors I was commenting before. 2 minutes, thank you. Regarding the economic, so I would like to highlight here the new processes that we have looking at for the recyclability, especially the one for using microorganisms to improve the recyclability of the metals, achieving values of 92% in the case of the Generation X batteries. I think I can skip that because my colleagues have already presented that, since I only have 1 minute. So I would like to highlight the exploitation survey or inquiry that we did in the consortium. which was with nice output. So the partners were very willing to participate and complement the results in new projects, which was great. Willing to the product innovation out from the developments that we have been generated in COBRA, aiming to make these products or this development commercial. And of course, we came up with many scientific papers, which are not detailed here because we have not closed the consortium yet, so I expect to do that when we close the consortium. And yeah, much willingness to get support from the market for the competitors and to have inputs from all the actors to really further develop the product. So just to finish up, very quickly, mid and long-term impacts, I wanted to just briefly summarize it, demonstrate the viability of cobalt-free. This is a new material we have developed on cathode, new sustainable that comes into play of the silicon, recycled silicon from PV industry, new ionic liquids have been developed, which the partners are willing to commercialize, which is good news. New pod cell components as well, new integration of foils, I was commenting, among other things. Enhanced smart sensors have already been implemented, so there are interest from the different players into the consortium to really explode that results and that to make that commercial. An improved battery management system is also is going to give you add value, hopefully into the market at some point. So just continuing with my colleagues, so we have managed to obviously to eliminate completely cobalt from the equation, and hopefully we are accelerating the implementation of generation 3B batteries for the near future. And from the studies of sustainability, at some point we will get the studies of this cost projection that we are having from the battery pack level at 2030. Thank you very much.
Thank you, Jordi. I would leave questions for later. Thank you. And last but not least, we have Intelligent, a last project that will be presented by Niels Peter Wagner from SINTEF, originally from Germany, but then moved to Trondheim to finalize PhD, and then you stayed there.
Yeah.
You liked it. So a PhD in material science from NTNU, Norwegian University of Science and Technology, where you are also adjunct associate professor now, and so coordinating this project Intelligent that will be presented now, following up a little bit the other projects, so midway, but with some results already. And we are willing to listen to it. So the floor is yours.
Is this my presentation? It looks so different.
You have to click here.
Yes.
Voila. And you can use it. And you
Yeah.
have 15 minutes.
I have 15 minutes. Thank you very much for the very kind introduction. Yeah, as you already said, our project is called Intelligent, which is short for Innovative and Sustainable High Voltage Lithium-ion Cells for Next Generation Battery, and it was spun out by the LCBAT5 cluster. So in comparison to all the previously presented projects, now we are in the Horizon Europe framework. Intelligent has a duration of 3 years, and it started in Q3 2024, so we are just about midpoint now. Our EU budget is 6.8 million euros, and we have 2 partners that now in this project have their own national budget, as they're not part or completely part of the Horizon Europe framework there. That's EMPA from Switzerland and the University of Oxford. The project is coordinated by us and SINTEF. We have in total 10 partners, which are 5 research partners and then 5 industrial partners. We have us coordinating the project and Vianode, our anode supplier from Norway. The cathode supplier is Topsoe from Denmark. Then we have Elite and Custom Cells as industrial partners from Germany, as well as Mio Battery from Spain, module integrator, and then it's EMPA, the Austrian Institute of Technology, IREC, the University of Oxford, and us as research partners. So Intelligent intends to develop safe, sustainable, long-lasting lithium-ion batteries with high voltage cathodes paired with a high capacity silicon graphite anode. So it all sounds very similar, and our approaches are also very, or like our targets are very similar. However, this project is a bit more focused and doesn't involve sensors or battery packs. So we do focus a little bit more on material development. However, at the end, we want to showcase this cell in 20 ampere-hour automotive pouch cell formats with high loadings beyond 4.5 milliampere hours per square centimeters, and also reaching a very high energy density at cell level of about 350 watt-hours per kg or 950 watt-hours per liter. The price tag should also be below 100 euros per kilowatt-hour, and we also have high charge or power capabilities as a target, and the cell should withstand 2,000 deep cycles, up to 80% residual capacity. So fortunately, we are not that far in the project yet, so I can't tell you yet if we will succeed or not. We cheer for it. However, these are very difficult to achieve targets, so we set ourselves also some technical objectives to achieve them, where the first one is the design of optimized high voltage electrolyte structures. So we have to balance the need for a very high amount of active material, yet substantial movement of charge, mass, and heat in the cells to really reach or balance the energy and power densities. We will refine approaches to stabilize interfaces for long cycle lifetime. So we often hear people talking about the cell chemistry, but what it mainly boils down to is the interfaces and the electrolytes to make this to work. The third technical objective is the scale-up of sustainable and low-cost manufacturing processes. So intelligent batteries will solely be based on aqueous processing, and we have a CO2 or like an anode with a lower CO2 equivalent compared to state-of-the-art. And then the fourth technical objective is the encouragement of industrial acceptance of our solutions together with our partners. We also have two non-technical objectives. Of course, it's to ensure compliance with the EU battery regulatory framework that sets the standards for sustainability within Europe, and to maximize our impact and encourage public acceptance of our solutions. So I can use that one as well. So if we jump over to the results presentation, bear with me and forgive me that I don't have as many results, or Intelligent doesn't have as many results yet as the other projects, but we have some. And I would like to kick off not with some graphs, but rather with an overview what intelligent batteries will look like. So we intend to build the intelligent batteries in 2 iterations or generations, where we have an interim scale-up that is to happen now in the next quarter. That will then consist of a silicon graphite anode delivering 450 milliampere hours per gram, paired with a surface-optimized LNMO cathode, which is aqueously processable. First generation of a high voltage electrolyte, as well as functionalized binders. We intend to have functionalities on the anode side that the binder can actually interact and graft to the SEI of the battery, but also on the cathode side that the binder is able to trap malign species, which sounds a bit like so-so, but what we mean by this is that all transition metal oxide cathodes will leach transition metals over the time, LNMO a lot, and these transition metals will interact with the SEI and will reduce cycle lifetime. We have learned that. So we would like to trap these transition metals in the cathode where they do not do any harm. The second or final generation then will be the full-fledged intelligent battery with an anode delivering 850 milliampere hours per gram and capacity optimized advanced LNMO, which is still aqueously processable. Our final intelligent high voltage electrolyte, and then full-fledged functionalized binders and also coated separators to further trap malign species such as transition metal, but also radicals and Lewis acids. We base this cell design heavily on model-based impacts, and then we want to upscale to 20 ampere-hour pouch cells. So the first thing I would like to talk about a bit is the cathode side of things, so our work on LNMO. So first of all, why do we work on LNMO, and why do I put it green? Now Boshida already told me that manganese might also be critical soon. Then we do not have that many metals left, unfortunately. But LNMO does substantially reduce the amount of nickel and lithium per kilowatt hour, while of course it's cobalt-free, it eliminates cobalt. And if we just see here, we see that the capacity of LNMO is actually quite a bit lower than regular NMCs such as 622 or 811. However, it also operates approximately 1 volt higher than these. And energy is, of course, the product of capacity times voltage, so the penalty in energy density is not as high as it looks. I would highlight the sustainability factor here, which we think is very important. And if we compare our LNMO to state-of-the-art layered oxides, we of course see that we are free of cobalt, we know that, and we also are much lower in the nickel content, so it's just a matter of time, in my opinion, that we also run into the same issues with nickel, because we're heavily based on manganese for now, which is hopefully still all right. But also to highlight that our lithium content in grams per kilowatt hour is lower. So this is due to the fact that LNMO is a spinel structure, which in comparison to layered oxides can be completely delithiated and relithiated in every cycle. So in layered oxides that Jordi and also Ruben already presented to you, we have what we call structural lithium that will stay in the structure. We need that for stability. The spinel is a framework and doesn't require that. So we want to base our cell on aqueous processing just to eliminate the need for having NMP in a battery, but also the heavily fluorinated polymer that we use, PVDF. And we got some inputs from an industrial advisor on some reference aqueous binder systems that they said work really nice for cathodes, and you see them here in orange. And our binder systems based on different bio and technical polymers already now outperform this, so this is really good. A further highlight here that we already achieved is surface optimization. Our colleagues from Spain have worked on coating the LNMO material with so far not a non-disclosed coating material, which also should mitigate transition metal dissolution and aid further the aqueous processing and also stabilize the system quite a lot. If we move further down the anode side of things, my favorite topic because it's so difficult, we're talking here about a low CO2 equivalent synthetic silicon graphite. So we expect to reduce the CO2 equivalent for these anode components in comparison to state-of-the-art materials by our partners' proprietary know-how, and also their process with a lower energy consumption. And the process is placed in Norway and based on clean renewable hydropower. We of course then eliminate natural graphite, and the first interim, I already said that is supposed to happen next quarter. And we've proven this first generation silicon graphite anode to be quite stable. So this is just the NMC based full cell versus the silicon graphite, and we have about 96% capacity retention. And the capacity is actually beyond spec. So we said we would have 450 in the first generation. We're here already at 550, and it works quite nice. Then to the most important topic, electrolytes. So the electrolyte of a battery, you can think of the cardiovascular system of a battery. We talk about materials, but it boils down to the electrolyte connecting that and carrying the charge carriers. At the same time, we already saw a lot of results, and it's very tedious to really characterize and optimize electrolytes. So what we base ourselves on here is what we call accelerated aging studies by cycling at a high temperature and harsh conditions, so at high currents. So we want the system to degrade, but we just see like which one withholds these currents longer on this temperature. And I have two examples for you here. The first one is on graphite LNMO pouch cells that were cycled at 40 degrees C, and here's a lot of different colors. The thing that I want to highlight now, in orange we have our, what we called our intelligent standard, our first electrolyte generation that we based our results on. And then in blue you see when we increased the additive to this, which had a profound impact on the cyclability. However, we had a slightly higher impedance in the cell and slightly lower initial capacity. And also in black, which is still basically the same electrolyte, we just replaced one of the solvents by another one. We saw a much higher cycle life. So there is a lot to learn still. But of course, we also look for the silicon graphite LNMO cells. And this is some relatively new results. And they were also cycled at high temperature, which is even more challenging for silicon-based materials. And in black and blue, you see our baselines, which were terrible. They basically died right away. But there's also, it just shows you there's a lot of resistance building up in the cell, because you can see whenever we switch the current to a lower current, the cell actually still has capacity, but the resistance in the cell is so high that the system can't follow. But also here we already have some interesting contenders, like in purple. We defined some new additives that we can add to the system that drastically increase the cycle life than here. As a last point, I'm not sure how I'm for time, I would like to briefly mention, 3 minutes, that's perfect, our modeling activities. So Intelligent is heavily based on model-based design optimization, and I'm sorry, I'm really not the best presenter for this, but we're trying to lower the barrier for model parameterization and increasing simulation time drastically. So on the very left, we see battery simulation platform that was developed within SINTEF, BATMO. And in the last 3 years, we managed to lower the time for P2D simulation down to 50 milliseconds. So we can really lower the burden that people say that these physics-based simulations are too time intensive. We do also digitalize and parameterize our cells. That we do so that we can also, like that we are conform to different modeling platforms, but also that we can use this parameterization to do design optimizations towards certain targets. So what we do here, for example, is the optimization of an LNMO graphite cell that should give us the highest energy density possible at a high rate of 5C. So traditionally you would model the whole parameter space here, which would be hundreds of iterations, but we use something, a method called differentiation, where we only model down a gradient line, and so we can reduce the amounts of simulations down to a factor of 10. So very briefly of our mid to long-term expected impact of the project. Again, I apologize, we're not that far yet as the other projects, but we work next to active material. We work heavily on advanced electrolytes and inactive materials to extend cycle life of high energy batteries by stabilizing interfaces and phases, and also by inclusion of new functional binders that can self-mitigate or heal components in the cell, which hopefully leads to broader acceptance and end-use uptake. We have sustainable electrode materials and processing, so which should result in less hazardous waste and lower energy consumption, and which also gives us industrial competitiveness. And as I now mentioned, we base ourselves heavily on model-based design, which then should hopefully give us faster development cycles and also improve performance, which also should lower the cost of research and give us a better competitiveness. And hopefully by the end of the project, we have intelligent batteries, which are European-sourced batteries with increased energy density and long cycle life, which should pave the way, of course, to independent and sustainable European battery value chain. That's a technical point of view. We can also quickly say we have a holistic point of view as well. So next to the technical things, of course, we have a societal impact, but broader acceptance of battery power and job generation. We also have environmental impacts by removing of harmful organic solvents from the electrode processing, and also removing fluorine, at least from the electrode structures. There's an impact on policy making by identifying high value to cost aspects, an economic impact, and an impact on skills. We have a high share of young and early career researchers within our consortium, and we also have what we call intelligent access, which opens our facilities or the partner facilities to external young researchers. That brings me to the end. I hope I was in time. I would like to thank, of course, the European Union for making this possible, and all my project partners, and you for listening. Thank you.
Thank you to our speakers. Thank you. So you see, very packed presentations, difficult to condensate years of work in 15 minutes. But I hope this was enough to stimulate you for questions, and I would also like to ask if there is any, let's say, technical aspects that you would like to ask our coordinators to address, so we can start with the question and answer session.
Okay, thank you. Since we don't have much time left, I don't want to steal your question and answer time actually, but just to refresh in our minds, I would like to give you a brief summary of what we have listened today. as you can see from these 4 presentations, the projects clearly actually serve the ambition on the reducing the burden on critical raw materials in line with the European expectations. So another important remark maybe from the projects wise is that all of these projects are complementary, dealing with the different challenges and building a know-how on the various aspects. Of course, for me it was really good to hear that all of the challenges in a nutshell was somehow covered within all of these projects, let's say including the volume expansion, the challenges we have facing with the low coulombic efficiency, and the need for the tailored binders and the electrolytes, etc. So in that sense, it's also good for us to see that this good work has been awarded with the follow-up projects with some of the partners involved, and also yeah, good. In line with this, it's also good to see that some of the partners will continue working on these specific issues. So with this description, I would like to open the floor for the question and answer session. So if you have any questions, you can, yeah. Sylvia, we can start with you.
Thank you very much. I'm Silvia Bodoardo from Polytechnic of Torino. Thank you for your presentation. I was quite impressed for very big results, but I have a question related to the reaction of LNMO with the electrolyte and production of methane that Boshidar showed us. So I guess the production of LNMO was with PVDF or water-based. And my question is if you have some deeper knowledge about the electrolyte used, so how to overcome this issue of methane production.
So the electrode processing on the cathode side was done both aqueous and with PVDF. So it was possible to effect this in both ways. So on the pilot line, aqueous based, but then for the upscaled process, we knew that it was not, let's say, industrially feasible or practical, so we stuck with the PVDF. On the methane generation, I mean, this is not my topic of expertise, but the base electrolyte was LiPF6, yeah, and then also with different additives. But for the follow-up work, how to mitigate this, I would probably refer you to our colleagues who are working on this, yeah. Unless anybody else wants to add to those topics, because I think some of the people here, some of the partners know more about these topics than I do.
Anyone who wants to comment on this? Okay, then we can proceed with the next question. Yeah, please.
Thank you. I have a question for the COBRA project. I think the project is well done. Congratulations. My question is about your system is monoclinic structure, cathode, and it seems to be working quite well with the system that you are studying. So, do you see any commercialization aspects of this specific cathode? And also, second question probably, what is the next step for your project?
I really like your question. Thank you very much for that. Well, generation 1 is really a composite, so we have a rhombohedral phase as well. So it's quite kind of a standard mode with some monoclinic phase. The generation 2 was really monoclinic, and it is really monoclinic, and we wanted to put more lithium there. But more lithium you put, more clinic it is, less well it performs, right? So I think there's a lot of potential for this material. So I'm trying to really push this material into other projects. If there are anyone who is interested to support this material, or any industry partner that is willing to look at this material carefully. More than happy to help and to support that. And the other question was the second step, right? On the in terms of material or in terms of the consortium itself? Well, yeah, thank you for that. Well, we are just now assembling the last battery pack with Gen X, and we only have to do the test, the electrochemical test and the safety test. So that is going to be the end for us. And quite happy, because I think this is what I have tried to show in the presentation. So we have achieved many specific objectives. So even though it is true that all our colleagues, we have been suffering, or we are suffering in terms of energy density and cyclability, but this is something I guess we all did, you know, so trying to push, okay, this is a major target, difficult to accomplish, but we can really focus on very specific target to really complement the value chain, the battery value chain, no? To make developments in many different points of the value chain, and I think we did. So I think we did. Thank you.
Thanks. Anything? Yeah, please.
Thank you so much. Thanks everyone. It was really fascinating being walked through your journey. Just a quick question, a couple of quick questions from Bashidar, and I just make a segue to broader questions about Generation 3. So 2 numbers in your presentation. The cost was $138 per kilowatt hour, and you had like 48 kilowatt hour per kilowatt hour of cell energy consumptions. So that's usually double the numbers that reported in the literature in terms of energy consumption. The cost is a bit higher than what's perceived as the $100 per kilowatt hour. Were there any specific reasons for that, or the simulation, how did it work out to get to those numbers? And given the capacities that was reported from 5 amp hour to 2025 amp hour, and given what's commercial in the market for other Generation 3 LFP, NMC moderate cobalt, I mean, that goes to over 100 3-digit capacity or over 60. So I think at the pack level, that would offset the small cells energy density. So I'm guessing my question is that there is a gap, and there seems to be huge, but what's your take on that gap, these chemistries that you're working on, and what's commercialized? I mean, is it more than what we expected to be, or do we need way more research into that? Or what's your understanding of that?
So regarding the manufacturing cost, what was looked at was starting from the proposal, the literature data, what was estimated by Bloomberg New Energy Research, and then we looked at what portion can be reduced through material cost reduction, what part can be reduced through automation, and what part can be also further improved through digitalization. So clearly there are possibilities on the material cost reduction through the substitution of the elements towards more manganese. Regarding the energy consumption per kilowatt hour of storage capacity, as far as I'm aware, the colleagues who modeled it said that it was actually very close to some of the literature values that they looked at. So the 42 kilowatt hours per kilowatt hour of energy storage capacity. The literature that they looked at, I don't know off by heart which one it was, but they said it was actually quite close, and we revised it upwards because in the first modeling it was actually below this value, but then inserting for some gaps where there was uncertainty, some of the literature values that raised it a little bit. Not substantially, but a small amount. Yeah. So I'm not sure I remember the second part of the question. What?
The second part is that if you take these numbers to be moderate or not really very ambitious, I mean, what's the competitive advantage of Generation 3B? Given that the LFP or cobalt are getting to a very, very good numbers. I mean, is there, that gap seems to be a bit significant. I mean, what's your take?
Yeah.
Anyone?
Yeah, I mean, I'll start and then maybe I'll let my colleagues answer as well. I think that the 3B generation has a lot of potential from the environmental perspective. For one part, that has not been fully realized yet. So we see that there are difficulties to meet all the performance targets. But if we are able to get to a place where this chemical configuration can actually perform well, and then scale this from a supply chain perspective, I think this is where the potential lies. So I would my take on this is the typical S-curve of technology. So established technologies are somewhere here. You have new technology development that's somewhere lower on the S-curve, but if you exploit it and develop it to its full potential, at some point it will surpass both technologically, ecologically, and hopefully also on cost perspective. So upwards potential still, yeah?
Maybe just to add, I mean, in the end, I think the energy density advantage still remains, right? Especially also compared to LFP-based cells. The environmental benefits Boshida talked about, and the other advantage I see is that it's a kind of plug-in solution, right? The technology is still relatively similar to, let's say, generation 3A or generation 2 lithium-ion batteries in terms of production technology, right? It's very, very similar. While when we are talking about solid-state batteries or lithium-metal batteries, there are much larger differences, right? Making it much harder to actually go from a coin cell to a, I don't know, 100 ampere-hour cell in high quality, high production yield and so on. So I think this is an intermediate step that makes a lot of sense, but of course, to really stabilize silicon is a huge challenge. That's why commercial cells so far mainly contain small quantities of silicon, not 10–15% yet. But if this challenge can be solved at some point, I mean, this would be really a plug-in solution that would significantly increase the energy density. And I think in terms of cost, we also did some modeling. It really comes down also to the cost of the anode material composite, or the cost of the silicon graphite composite. And there are some estimates that those materials are not necessarily much more expensive than graphite. And that's important, right? And in the end, you need less in terms of weight, significantly less compared to graphite. So maybe there's, in the long term, even a bit of a cost saving there, especially per kilowatt hour. So yeah, I think there's a lot of potential.
Anyone who wants to comment on it? Then we can go with the next question. Yeah, please.
So your projects have shown that electricity is not.
I'm sorry to disturb. If you can introduce yourself before.
Yeah, Christoph Scharnus from FEV and ERPA. Your projects have shown that electricity is not the only thing expensive when you go for fast charging. Did you make any investigations how long your cycle life lasts if you go to lower C rates than the 2.5C or 3.5C that were requested in the topics?
Who wants to take it?
I'm going to take this difficult question then. Actually, in our case, the test, frankly speaking, in our case in COBRA, the test that to achieve that ambitious cycle life, 2,000 cycles, were not done at 1C or 2C, but were done at much lower C rate. This is clear. I don't know about the other ones, but full stop. So.
I mean, I can confirm we start with 1C, but if the performance is already lacking on the cycle life, then there was not much point to try for cycle life at 2.5C. In any case, the fast charging was supposed to be intermittent, so I think 10% full cycles or 10% of the cycles in deep discharge were supposed to be done at 2.5 or 3C, but in our case with the gassing of the cell, this did not make so much sense.
Thanks. We can go with the next questions. Yeah, please.
This is Pietro Perlo from IFES. The first question is for the three presenters. You referred to the C rate as a number. Now, I'm talking as a user, okay, as an end user. If I know the C rate at 50% state of charge is one world. At 20% state of charge is a totally different world. So you cannot discharge at the same rate because you immediately destroy the cell. So what it is really important from an end user point of view is not presenting the C rate as a number, but as a function. This is for the three presentation, for the first three. For the third presentation, just one consideration. Aluminum is totally transparent to low frequency radiation, magnetic field, 150 Hertz. So whether you like it or not, if you want to protect the passenger and the driver from low frequency magnetic field, you need a top layer in steel. And as an end user, I can contest a little bit your statement that you can reduce 50% the weight because as a structural mechanical, I am a physicist, but I am also a mechanical engineer. And mechanical engineers know very well that per the same strength, super high strength steel is much lighter than aluminum. So if you take a solution in aluminum, I can make it lighter in steel per the same strength. But the steel, as I told you before, protects the passenger and the driver from low frequency magnetic field. So if you want to make a safe pack, you need to use a top layer on steel. That's what Tesla and many others are doing.
Thank you for that. I was totally unaware about that, so I will transfer your thoughts and comments to the partner corresponding to that. Definitely, I think it's something to write it down and to consider for my short knowledge into battery pack assembly. Thank you.
Anyone who wants to comment on this?
Yeah. Yes, no, I think I agree with you. I mean, on the lab scale, most people just really apply a C rate. I mean, they still do CCCV, right? Constant current, constant voltage charging. But I know that the commercial battery pack is charged in a different way, right? You ramp up the current and maybe you reach a maximum current, and at very high states of charge, you ramp down the current again, right? Because you have to follow the resistance as a function of state of charge of the battery, of course, right? Typically, the resistance is high at low and high state of charge and lower at intermediate state of charge. That's why you cannot come with your, I don't know, maximum current right from the beginning. But this is usually not done, let's say, on the coin cell level when you develop materials, right? Because these resistance limitations become much more important on the pack level. There you also have to you have issues with the heat dissipation and so on that you don't have on a very small scale and so on. So yeah, it's not yet standard, I would say, in the materials development community to use such a complex charging function, because it's not really necessary. But of course, one then has to see how does the behavior on the materials level, on the coin cell level, translate to the cell level, to the module level, to the pack level, and so on, right? I mean, it doesn't translate necessarily one-to-one, and then it's also really a lot about engineering. I mentioned heat dissipation and so on. So these are all very important questions that especially companies look very much in detail into. I'm sure about that. So thank you for the question.
Maybe I can just add very briefly on top of what Ruben said. So this question, let's say, it can also be transferred as regards the end user to the logic and the intelligence in the battery management system. So this is, okay, we don't show it on the lab scale like this in materials development, but in the BMS, sort of the dynamic adjustment of maximum charge and discharge currents in function of internal resistance, temperature, etc. This is something that can be done and is being done at least experimentally in the BMS. I'm not aware how far this is already applied commercially, but as far as I know, I'm not expert in BMS, but these values, let's say, where thresholds are pre-parameterized, and in future they should be dynamically ascertained based on sensor information, for instance. So this is also something that we have looked at a little bit in the project, but there was not time to talk about this also.
Thanks. Any questions? I think we have one here, just in the third line.
So my name is Erkan Öterküş from University of Strathclyde in Glasgow. My question is actually to Niels Peter. You mentioned about these physics-based very fast simulations. So can you provide more information about actually what type of simulations are they?
Yeah, we're talking about Newman simulations in P2D, P3D, and P4D, but I, in all honesty, have to admit that I am not the expert in the consortium doing this. But if it's of interest for you, I would ask you to send me an email and I would forward you to the people that actually work with the modeling. I'm a chemist, so I'm usually more in the lab.
Please.
Hello. I'm Joshua from CITEC. I'm collaborating with Jordan in COBRA. One question of the sensors, okay? I think in 3 of the 4 projects, sensing is an activity. You have used different sensors. I understand fitting the BMS. Which are, let's say, the advantages, or which sensor would you use for your BMS from the spheral ones that you have implemented in each case? Thanks.
Okay, so maybe I will start the answer. So as you maybe remember, we looked at 3 different sensors in the 3 Believe project. So one was the internal ones on a fiber optic basis, which basically measure the change in light wavelength and look at very localized effects inside the cell. And then the other one was a multi-measurand kind of sensor, which measures several parameters, and it's essentially on the cell and connected to the tabs. And then the third one was the module level sensor, which is, let's say, quite standard, but was improved to automotive standards. So to answer your question, the one that we take up for further use in projects is the middle one, so the multi-measurand on-cell sensor, because it has some properties that can be interesting or can deliver information that could be interesting from a safety perspective. So for example, strain, gas evolution, wetness, electrical impedance. As I pointed out in the presentation, the optical one, okay, it was possible to integrate it. The integration effort is doable on a manual basis, but for automation it's quite difficult. Let's say the optic fibers are quite finicky, and it's not yet so clear how to correlate the data from that sensor to the electrochemical measurements. So what is the sensor really telling us? So that's why it was, let's say, not recommended from our perspective that it should continue for in-cell sensing.
Yeah, I would say in the end it really comes down to costs, right? I mean, cells, especially for the automotive industry, are extremely cost-driven. We all know that. So maybe even a cheap sensor is too expensive, perhaps. I mean, you really have to demonstrate a clear benefit, right? If it enables a technology that cannot be used without sensors, maybe then it's feasible. But if it's not really necessary, it might be too expensive. But I think it's a great tool to better understand cells. So it's really a great tool in the development phase, I think. If you can, for example, map the temperature distribution in a cell, I think this is very, very valuable information when you are designing your module or pack, right? Coming back to the heat dissipation. So I think it's a great tool, but if we will really see, especially in-cell sensors in mass market applications. Personally, I'm a little bit skeptical due to the cost argument, but I think in R&D it's great.
Just to add, I was just thinking what to add. Yeah, I think no, I think the argument of the cost is, to me, I totally agree with that. In COBRA, as you know, we have integrated many sensors, and all of them, it has like a very important function, and eventually we have demonstrated, like, or we will just, in a question of weeks, you know, like a whole module with a safer, a more efficient and highly performant module, I would say, coming from the Gen X. So, my preference, I don't know now. I think there is a big concern in safety. All sensors are important for safety, obviously. I think it is important. Gas detection, I think, is quite relevant. We saw many late calls from the Commission. You know, much more focus on that sense. You know, in gas detection, especially said for the safety of the, or improving the safety of the battery. So. But I guess eventually, you know, I agree. So cost and requirements, what battery are you using and for what are you going to be using that battery? It's going to be the key point, right?
I agree with all what you said, and in Intelligent, we were so lucky that we were a bit more focused and did not focus on sensors. And so in Intelligent, we were fortunately so lucky that we didn't have to focus on all the aspects, so we boiled it more down that we really want to focus on the cell components itself and left the sensors to the mother projects, so to speak.
Okay, thanks. Before wrapping up, I have a very small question which I ask a contribution from all of the partners, all of the projects on the table, which is also a very small question in order to set ourselves a baseline for it. And what is the content of the silicon you are targeting in your projects, and what is their dimensions? The dimensions, it's a nano silicon or micro level. What is the particle size mean?
We can start from the back maybe. So Intelligent is based on nanosilicon, a composite of nanosilicon in a graphite host. But all the details, that is our partner, and I don't think they want to disclose everything about it, but it's nano submicron to nano sized, yeah.
Thank you, Niels. In COBRA, we are working with micro silicon, and we have around between 10 and 12% weight of the anode.
In sense, it was nano-sized silicon material, so silicon graphite composite material, and the silicon content was 10 to 15%.
In 3 Believe, we examined between 15 and 40%, but finally we remained at the 15% silicon graphite composite. I think our partner also did not disclose the exact details, but yeah.
If I may also add, what we did in Intelligent, which is probably a bit different to the other projects, is that we did not define the content of silicon, but rather the capacity. We know the boundaries, we know the theoretical limits, and we said, like, in the end, if we reach this capacity with more or less silicon, it does not really matter, but it doesn't constrain us that much that we said, like, oh, we promised to use 20%, and now we have to explain to the Commission we only use in 15%. As long as we meet the metrics, I think it is not really that important how much of the material we use.
Indeed, totally understood. So yeah, we come to an end to this session. I thank you for all of the participants today, especially from the projects we're sitting on the table. And thanks again for these presentations.